Greetings and welcome to the PL/SQL channel, a series of video trainings on the Oracle PL/SQL language. My name is Stephen Feuerstein, and I'm a PL/SQL developer just like you. This lesson is part of my series on programming with collections, Oracle's array-like structures, and the focus of this lesson is string indexing and associative arrays, a very fascinating and relatively advanced topic for PL/SQL developers. Some quick reminders. Download all the code and PowerPoint supporting this training at PL/SQL Obsession, otherwise known as toadworld.com/sf. Let's take a quick look. PL/SQL Obsession, lots of resources for PL/SQL developers. Click on the demo zip link to download a zip file that contains all the scripts that I run during this lesson and all my other lessons. Click on training, seminars, and presentations to have access to all the PowerPoint presentations that back up and support my lessons. In addition, make sure you're comfortable with the material covered in the previous lessons in this series. How to define collection types, using collection methods, working with associative arrays, and non-sequential indexing in associative arrays. All of these lessons will be critical to making the most out of this upcoming lesson. So what I want to talk about are the extended indexing capabilities for associative arrays, and most importantly, the ability to index by strings. So prior to Oracle 9i Release 2, a while ago now, you can only index by a binary integer, which means, to be very specific, that if I was defining an associative array type, let's take a look at a simple example. Here's a collection or list of names indexed by integer. Prior to 9.2, it had to be indexed by binary integer, which is a subtype of the integer data type that only supports values between -2 to the 31st plus 1 to 2 to the 31st minus 1, so a subset of the integer type. Now, you can define an index on your associative array for any subtype derived from binary integer, and more importantly, varchar2s, strings with a length between 1 and 32,767. You can also do a index by on a percent type against a database column that is consistent with the above rules, meaning that you can index by percent types on varchar2 columns and subtypes of anything of the above. The most important thing is you can index on string values. If you have concatenated indexes in your table, you can combine all those indexes together into a string indexed by that, and so on. So all of these variants are supported for index by clauses. Binary integer is the original. You can now, and probably should use in its place, PLS integer, which is roughly synonymous with binary integer, but is supposed to be at least a little bit faster under some circumstances. I really doubt it makes any difference in your index by clause. It looks like more modern PL/SQL if you use PLS integer as opposed to binary integer. There are other subtypes of binary integer like positive and natural that you could use, but really that's not that important. Whether you declare it as binary integer or PLS integer, it's roughly the same. The big advance in 9.2 and above, and the focus of this lesson, is indexing by varchar2. I can have an explicit declaration. I can also use a percent type or a subtype against some previously defined type. So all of these things are possible, but the real question is, how do you take advantage of this interesting functionality? So let's take a look in more detail at working with string index collections. First of all, the syntax for using string indexing is pretty much the same as integer indexing. All the same methods are available. The basically the same code will be written. The only difference is that your indexes are strings, and as a result, the type of data returned by the first and last methods, the next and prior methods, are strings rather than integers. And the other thing to keep in mind is that the longer the string values, the more time it takes for Oracle to hash or convert that integer into a string, the string into an integer that is actually used as the index value. So under the covers, these collections are always indexed by integer. Oracle just makes it easy for you to specify a string. It converts that string into an integer, which is hopefully unique and not currently occupied or already used, and Oracle just manages all of that for us. Let's take a look at some examples and also the issue of the overhead of converting from string to integer using the string indexing. So let's take a look at the associative array 1 script. Now in this example, what I'm going to do is keep track of countries and continent populations by their name. So rather than build a list of all the countries and continents in the world and associate with those countries and continents rather than build an array that is filled sequentially with countries and continents and include their name and their population, what I'm going to do is create a new type of data, which is a table of integers, the population, indexed by the string, the name of the country or continent. So I've got a country population list, a continent population list. I've got a variable that tells me, for example, how many I've got if I do a count. And I've got my index value, which in this case is a string. So just to give you an example of the syntax, the kind of code you would write, it's no different than what you would have written for integer indexing, though it can look different. I'm going to assign the value of 100,000 to the Greenland location in my country population list. I'm going to assign 750,000 to the Iceland location in my country population list. So Greenland is the index value, that's the location in my list. Iceland is the location in my list, and these are the values that are stored in it. And I do the same thing for continent populations. Australia, Antarctica with an uppercase A, Antarctica with a lowercase a, New Zealand. Now this looks kind of funny because I've got hard-coded literal values, strings, inside my parentheses. But usually it would look like this. That's my index value, whatever it's set to. I assign 100,000 to it. This looks just the same, whether it's an integer index or a string index. And that's mostly what your code will look like. In other words, the data type of the indexing is often hidden from view in the lines of code that you write to manage that index. But in this case, I state them explicitly. You can see that they're actually strings. And now let's ask some information about this collection. First of all, how many have I got? I call the count method. That returns an integer, just as it does for integer indexing. Let's find out the population of Greenland. In this case, I pass the word Greenland as a string to the location array, to the array of countries. It goes to that location in the list, and it returns the population. I get the first defined element in my collection. I assign it to index value. Remember, that's a string. So first is now a string. I display it. I display last, first, and last in my continents. And let's see what I get. I run my code. Look at the results. And my count is 2. So the count inside the country population is 2. The population of Greenland, so I passed in Greenland. It returned the population is 100,000. The first row defined in my continent population list is Antarctica with an uppercase A. The last is Antarctica with a lowercase a. And that's because I'm using the default character set in Oracle. It's using the ASCII ordering to my characters, and lowercase comes after uppercase. The meaning of first and last and next and prior when you're using string indexing is determined by the character set you're using. So it's not necessarily intuitive as to what that ordering might be, but it should make sense within the context of your character set. So that's, as a quick glance, what is involved in working with string indexed collections, which is it's no different from integer indexing. The only difference that we've seen so far is that the value returned by these methods like first and last, next and prior, are strings. One thing to also remember is that if you're working with string indexing, you should never ever try to iterate through your collection using a numeric for loop, going from first to last. These are now strings, and unless they evaluate to numbers, integer values, you're going to get an error. So when I try to do this, I get a numeric or value error, character to number conversion error. It tried to go from Antarctica with an uppercase to Antarctica with a lowercase. Those are not valid integer values, and therefore an error is raised. So when you're working with string index collections, you always need to use the while loop. Go from first to last, start with the first or last, and go to the next or prior using these methods. In fact, let's pull this over into the other script and we'll try it out. So let's do this. Iterate through and show all the values in my collection, but not my happy family. Let's do continents. So population at. So we'll take a look at the population at the index, whatever the name is, equal to that value. And in fact, it's at the continent in continent. I'll get there eventually. Okay, let's try this code. Run my script. Whoops, I didn't replace all the values of my names. There we go. Try it again. Now I got a numeric value error from the for loop afterwards. Let's keep going. Let's take a look at what we've got here. And notice, here are the populations in the 4 continents. So I did a loop through my collection, retrieving each individual element from lowest to highest, using first and then next. But if I tried to use the for loop, I got the exception. So let's just put that back in its own little comment. Whoops. So, when you're working with string indexing, you need to make sure you remember that the first and last, next and prior return strings. When you're iterating through a string index collection, you have to use something like the while loop or the simple loop. Never use the for loop. Okay. Let's talk about the performance penalty. Let's look at the associative array performance test script. Now what I've done here is create a program called associative array index test. I pass in the number of times I want to run my code, the length of the string I want to index by, or the length of the string I'm going to be using. I've declared 2 different collection types, indexed by integer, indexed by varchar232k, each of them collecting records of the employees table. And then what I'm going to do is test the performance of populating my collection. Let's see, first of all what I'm going to do is populate each of my collections, integer indexing array, string indexing array. I'm going to copy the record into my collection using the primary key as the index value or the last name padded to a certain length. So basically I'm going to create string indexing values that have a certain length. So if I say I want lengths of 10, it would have just 10 or 100 or 1,000 and so on. And then what I'm going to do is use my timer object to start my timer, run my code n number of times, which means essentially get all the data from the table, and then look up the value in my array structure and assign the salary value. It doesn't really matter what I'm doing there. What matters is that I'm using my integer indexing versus my string index. And then I'll take a look at the performance of each one at these levels, 10, 100, 1,000, 10,000 characters. Now I encourage you to try this on your own. I'm not going to run it again now. I ran it this morning, in fact, and here's what I found. Essentially, when I do integer indexing for my 10,000 iterations, the performance time for the by integer index is about 2.7 seconds all the way through, 2.7 more or less. The performance time to do my string indexing increases, often dramatically, depending on the length of the string. So if I have a length of 10, a small string, notice my performance is just about 3 seconds, so it's certainly more expensive than integer indexing, but not that much more. When I went to length of 100, it went up a bit, not too much. When I went to 1,000, you can see now it's over 4 seconds compared to under 3, and at a length of 10,000, my string to integer conversion was quite expensive. So the point that I'm making here that you should keep in mind is that string indexing for relatively small strings is quite efficient. You don't pay much of a penalty at all by moving to string indexing. But as your string gets bigger and bigger, you can expect to pay more and more substantial of a penalty in terms of the overhead for looking up that data and managing the data in that collection. Let's take a look at what I would consider to be a practical application for string indexing. I've been involved in writing an application for Quest software called Quest Code Tester for Oracle. And Code Tester for Oracle is a tool that you can use to automate the testing of your PL SQL code. Here's the dashboard. I'm not going to go into the details of it, but let's take a look at why I needed to use string indexing. So you can run your test and it automatically generates your test code, and then it runs the test and verifies the results, and isn't that great? Okay, here's my program, between string. And I pass in a string, a start, an end value, and inclusive. It has parameters. And you don't have to do this, but instead we do it for you. We generate the test code that is executing to verify your code. So here's an example of the test package. Lots of code. Again, it's not something that the user has to worry about. We generate it. And I wrote a package to generate the test code. Now, one of the things I do is generate local variables for each one of my parameters and for a bunch of other things as well. So part of the dynamic test code generation is generating variable declarations. Now, as I'm sure you know, you can't have multiple declarations with the same named variable in your block of code. Oracle will raise an error, raise an exception. So when I do my code generation, what I need to do is keep track of the names of the variables that I've already declared, so that if I try to declare a second variable with the same name, I've got a complex situation with multiple sets of variable names coming in from different places. If I find that I'm about to generate a declaration with the same name of something I already generated, I want to skip it. Don't regenerate that declaration. To do this, I need to keep track of the variable names that I've already used. So the algorithm needs to be something like this. For each of the variables I've got defined in my collection, if the variable name is already in use, do nothing. Otherwise, add the variable declaration and then mark that variable name as being used. So, there are lots of ways to do this to keep track of the resources I've used. But in this case, string indexing collections makes it really, really easy. So first of all, what I'd like to do is talk about building the string tracker package, this utility that will do this for me, without using string indexing. Now, generally speaking, two subprograms are needed here. One is called string in use. Is the string in use? It returns true or false. Returns true if the string was previously used. Mark a string as used. I mark the specified string as being used. So that's basically the API, the programs I need to build. And the most obvious implementation is to create a collection to track the list of used strings and then see if the string is already in use. And then I'll search through the list for a match. Let's take a look at my string tracker version 0. So in my package specification, I declare my string is in use, pass in the value or the name, return true or false. Mark a string as being used, pass in the value, and mark it as being used. How do I do that? Well, inside my package body, I have a list of string names indexed by PLS integer. This variable name, by the way, is a subtype. It's a type based on another type.